Grade 11, single phase transformers. Before we get to the transformers, there's a couple of rules that you guys need to remember. Firstly, Lenz's law. Now Lenz states that a change in current will produce a voltage whose direction is such that it opposes the original change in current. What that basically means is that if I have an increase in current, it'll create a decrease in voltage, because the decrease in voltage will oppose the original increase in current. Okay, now we're still going to get into that, but what we need to realize what this actually means is that if I've got a graph and I compare my voltage to my current, if this is the current that's flowing in my coil, what it means is this increase in current generates a voltage that opposes that original change in current, which means my voltage graph is going to look like that. If those two lines are in phase, those two are in line, those two are in line, those two are in line, and those two are in line. No, I'm sorry, that's wrong. If I compare my voltage and my current on a graph, if I supply a sine wave as the voltage, what that means is my current is going to occur 90 degrees after my voltage. Alright. This is basically because when I've got an increase in voltage, my current wants to increase. But because the current wants to increase, it generates more magnetic fields. And because there's more magnetic fields, my current actually delays with reference to the voltage. So when my voltage decreases, that allows my current to increase. That is Lenz's law. Next, magneto-motive force. Or MMF. Magneto-motive force is the field strength that is going to be developed when I pass current flow through a conductor. So MMF is basically the resultant or the product of my current and the number of turns. My magnetic field strength my magneto-motive force is measured in ampere turns. The magnetic field strength that is going to be generated, symbol is H, and that is equal to my magnetic motive force divided by the length of the conductor. So the shorter my conductor is, the more or the stronger my magnetic field is going to be. Now when we look back here, and I said that this voltage increases, my current wants to increase, but because of the increasing voltage and the generation of the magnetic field that causes this delay in the current, that is called my self-inductance. Okay, now to calculate the self-inductance of a coil, we have a couple of formulas. Okay, self-inductance, or L, is equal to the number of turns divided by, or multiplied by the flux that is being generated, divided by the length that is that the coil is, and this is measured in Webers per meter or Henry. Okay. Second formula is a more accurate formula. Firstly, we've got the Mur symbol. That Mur symbol refers to the type of core that I'm using. N squared refers to the number of turns. A is the cross-sectional area of the core, and then again L is the length of my coil, also measured in Henrys. Okay, now looking at a transformer, it works on the principle of mutual inductance. Okay, so basically what happens is I've got one coil, we call this my primary turns, and I've got a second coil, we're going to call this my secondary turns. Now, in grade 10 you learned that when a conductor experiences a change in magnetic field, that it will create a voltage. So what happens over here is I am going to supply my primary turns, or my primary coil, with a sine wave of voltage. Call this the primary voltage. So what happens is this voltage will create a current. That voltage will cause a current to flow through that coil. Call that my primary current. Because there's current flow, again, you've got to remember that the current is 90 degrees after the voltage. Because there's current flow, we will generate a magnetic field. The size of this magnetic field is directly proportional to the size of this current that's flowing. So, if I have an increase in flux or in current, I will have an increase in flux. Okay. Now, as this magnetic field increases and decreases in size, this second coil will experience this exact same magnetic field, but in the opposite direction. So as this decreases from negative maximum to 0, this side will experience that magnetic field as a maximum falling back to 0. And then as it goes on over here, it will go in the negative and then again into the positive, giving me a secondary magnetic field experienced like that. Because I've got this magnetic field flowing, if this circuit is closed, I will generate a current that flows through there. That current is proportional to that magnetic field. As a result, I will get that cos wave for my secondary current. Because I've got current flow through the load, or the resistor, and because I've got current flow through the coil, I will develop a secondary voltage on my coil. And that secondary voltage will look like this. Okay, what we see over here is that my secondary voltage is the reverse of my primary voltage. That is because of the phase shift capabilities of the coil, which we'll get into at a later stage, as well as the direction of the magnetic field. As this magnetic field increases in this direction, this coil sees that as a reverse or a decrease in magnetic field, and as a result we get the reverse voltage observed over there. This is mutual inductance, and this is exactly how a transformer operates.